exhaust gas from the engine, the Kc is 4.2 times 10 to the minus 8. The chemist puts 0.085 moles of nitrogen and 0.038 moles of oxygen in a rigid 1 liter cylinder. What is the concentration of nitrogen monoxide of the mixture at equilibrium? So this one's a little bit different. Okay, we're given the Kc value. Okay, and then we need to solve for one of our numbers at equilibrium. So again, we always start with a nice table. I'm going to write that out. Just pause it here to make the video a little bit shorter. Okay, this is what I got so far. So we have our balanced chemical reaction. One thing to know is this is not balanced, so always check and make sure it's balanced. Okay, then we write down our initial. So we're given our two initial. We're given moles. We have to divide them by liters. Since it's 1 liter, they're the same number. Okay, and then initial amount of product is 0. Okay, our change, these are going to be minus x, and then plus 2x. Then we're given our Kc value. Okay, and so again, for this one, if we work it all out, we're going to get a quadratic equation. So the thing we start with is figure out a rule of 1,000. So rule of 1,000, we take our initial concentration. Okay, we're given two different initials. Okay, pick one of them and divide it by our Kc value. Okay, so I usually write it off on the side here, kind of just saying rule of 1,000, take an initial. Again, they're very, either one you use, it's going to give you a large number. Okay, when you divide this out, all you have to do is say that this number is greater than 1,000, which means now I don't have to worry about these minus x's. So this number is going to stay at 0.085. This number is going to stay at 0.038. Okay, and then this will be plus 2x. Okay, now we need to solve for x. Okay, but we don't have, I don't know what this equals. Plus 2x equals what? That's what I'm solving for. Okay, the way I do it is writing out my equilibrium formula equation. Okay, so that's what I've written out here. Now I can put in my numbers because I know this number, I know this number, I know this number. I need to solve for this. And so I just put those numbers in and I'll do that and then we'll solve for it. Okay, so the numbers are now in there. So now we're just solving for x. Okay, and so we'll do that next. Okay, so this next step, I just did 0.085 times 0.038. And since we're dividing by them, we have to multiply both sides by them. So I'm going to multiply these two numbers by this number. I get 1.36 times 10 to the minus 10. Okay, that's going to equal 4x squared once I bring the square into both these numbers. Okay, now I'll divide both sides by 4. And I want to square root both sides. Okay, to get rid of the square root cancels with this, the 4 cancels with this, so then I'm solving for x. Okay, so my x is equal to, okay, so my x is equal to 5.8 times 10 to the minus 6 moles per liter. Okay, I want to solve for this number, so I just times that by 2. And I get 1.2. So my concentration at equilibrium, okay, I have my NO, is equal to 1.2 times 10 to the minus 5 moles per liter. And that would be my final answer there. Okay, on to the next example. So this one, any of these that, say 15.2, they're kind of in the blue, they're all out of your textbook, so you can check on this one. We'll do it and make sure, and so you can just make sure it's done right. But if you ever want to see more examples too, your textbook's a good place to go. All right, I'm going to do this example on a notepad just because there's not a lot of room on the sheet that I have. Okay, so we have in a 500 milliliter stainless steel reaction vessel, 900 degrees Celsius, carbon monoxide and water vapor react to produce carbon dioxide and hydrogen. Okay, evidence indicates that this reaction establishes an equilibrium with only partial conversion of reactants to products. Initially, we have 2 moles of each reactant is placed in the vessel. The Kc for this reaction is 4.20 at 900 degrees Celsius. What amount concentration of each substance will be present at equilibrium? Okay, and so again, first step for any of these problems, balance chemical equation. Okay, so I'll do that to start with. Okay, so here's my chemical reaction. Okay, so we have carbon monoxide plus water vapor, produce CO2 and hydrogen gas. Make sure you remember hydrogen's H2. Okay, and I wrote down the Kc just to kind of remember I have that number too. Okay, now I'm going to set up my ICE table, okay, and write in the numbers that I know. Okay, so I have my ICE table set up here. So up here, I just want to write down like these are the concentrations in moles per liter. Again, the square brackets here just mean concentration. Okay, and then I don't have to write in moles per liter for each one of these. Okay, to solve for the concentrations, I have to use my moles divided by my volume. So I'm given my moles here is 2, volume is 500, okay, or 500 milliliters, so I convert that to liters. Okay, and I got 4 moles per liter for my initial for both of these. Okay, next I'm going to write in my change. So both of these are going to go minus x, and these are both going to be plus x. Okay, like that. And so now I write down what I have at equilibrium. So this is 4.00 minus x. This is 4.00 minus x. This will just be x, and this will be x. Okay, one other thing to note is like if you did the rule of 1000, which we can do right now, so rule of 1000, okay, it's not going to work for this one, but we'll just do it to show you how. So again, you want your initial 4.00 divided by your Kc, so 4.20. Okay, this is going to be less than 1000. Okay, doing it like it's going to be 4 divided by 4.2, 0.95. So yeah, like nowhere close to 1000. Okay, so I can't do that. Like I can't use this and get rid of these x's. Okay, but one thing to note for these types of problems, these are the same, these are the same. So when I set up my Kc expression, so my Kc is equal to CO2 times H2 over CO times H2O. Okay, I can put my number or my values in. On top, I'm going to have x times x. On the bottom, I'll have 4.00, or whoops, minus x and times 4.00 minus x. Okay, and so really what I have is Kc is equal to x squared over 4.00 minus x squared. You have this like same two numbers on top, same two numbers on the bottom. Okay, so now to solve for x, oh, I should put in my number here. So I have 4.20 is equal to x squared over 4 minus x squared. Okay, if I want to get rid of the squared, I can just square root both sides. Okay, so I get now 2.05. Oops, I'm running out of room here. 2.05 is equal to x over 4.00 minus x, okay, which now gets rid of our squared problem, and like it makes it a lot easier to solve for x. Okay, so now if I want to isolate x, I'll times both sides by this 4.00 minus x. 4.00 minus x is going to be multiplied by the 2.05. And so I get x is equal to, I just flip this equation around, this is the same x over here. So now 4.00 times 2.05, I get 8.20 minus 2.05x. Okay. Now I'll just add plus 2.05x to both sides plus 2.05x. So I get, remember there's a 1 here, so I get 3.05x is equal to 8.20 divide both sides by 3.05. And I get x is equal to 2.69. Oh, there we go. Okay, so this now, like, it gives us these numbers for x. So now I can just solve for all of these. And so I want, like, at equilibrium, what are my numbers? So I'll kind of write that just down underneath here. So 4 minus 2.69, I get 1.31, 1.31. This would be 2.69, 2.69. Those would be all my numbers at equilibrium. Okay, so this would be my final answer. Okay, in the textbook, they draw a whole nother ice table. I don't need to see that. I just need to see that, like, you found, like, this is my answer here. All right, got a couple more examples here. Okay, so the next one, we have 5-liter reaction vessels filled with 6 moles of HCl and 2.5 moles of oxygen. Okay, at equilibrium, it was attained according to this equation. So this is our equation. This should be a two-sided arrow. Okay, and at equilibrium, the vessels found to contain 1 mole of chlorine, or Cl2. Determine the equilibrium constant for this equation. Okay, so again, write out our equation with an ice table. Okay, I have my ice table. So our initial, again, we're given moles, so we have to go 6 divided by 5 gets 1.2, 2.5 divided by 5, we got 0.50. Here, initial for products are 0. Okay, we write down our changes, again, using our coefficients to see how much it changes by, and then write down our equation. So 1.2 minus 4x, 0.5 minus x, plus 2x, and then here, we're given that at equilibrium, we have 1 mole of chlorine, so we know that that's 0.2, so we know 2x is equal to 0.2. Because we know this, we can now solve for x. Okay, and so 2x equals 0.20, and we'll divide both sides by 2. And so we got x is equal to 0.10. So now from that, we can we'll write down our numbers. I'm just going to write another E to kind of say at equilibrium what our actual numbers are. So we're going to put our x value into each of these. So like we already know this one, 0.20. This one would be the same because we have the same value here. So this is 0.20. Okay, we have 0.5 minus 0.1, 0.40, and then 1.2 minus 4 times 0.1, we get 0.80. Okay, now we know all our numbers at equilibrium. We can now solve for our equilibrium constant, which is what we want to solve for. So our equilibrium constant, Kc, is equal to H2O squared times chlorine squared over HCl to the power of 4 and O2. Okay, we'll put our numbers in for all of those. Okay, so put our numbers in, and now just solve for our Kc. Put it into our calculator. Make sure, try these at home. Make sure you're getting the right number on your calculator so you get the right answer on your put into our calculator. All right. Last example we'll do on this video, okay, is a backwards ice table. Okay, so in this case, we have hydrogen iodide gas decomposes to hydrogen gas and iodine gas. So we have Hi is going to produce H2 plus I2 gas. So that's where we start. Okay, if the final concentrations of hydrogen and iodine gas are 0.10 moles, so we have our final concentration, our equilibrium concentrations, and the final concentration of hydrogen iodine gas is 0.2, then calculate the initial concentration of hydrogen iodide gas. So again, write out our ice table. Okay, put our numbers in. So in this case, we have hydrogen and iodine gas. Oh, we need to balance it. We need a 2 over here. Okay, so these are both 0.10 or 0.010. Okay, we're looking for this. This is kind of our unknown. This is going to be 0, 0. This would be plus x, plus x. Next, yeah, so basically x is going to equal this. This number is going to be minus 2x, and then, so like our unknown, so I'll just say like our initial concentration of HI minus 2x will give us this number, which is 0.0020. Okay, so now, like, once we know what x is, which we know from this, we can put the number in for x. So our initial concentration of HI, I'm just going to put an I there for initial, minus 2x is equal to 0.020. Okay, so now we know what x is, so we can put that number in and then solve for our initial concentration. So we'll do that. HI initial minus 2 times 0.010 equals 0.020. Okay, so we got this, solve for this, put it in. Now we're going to add 0.020 to both sides. So our initial concentration of our hydrogen iodide is just going to be 0.040. And I guess we need moles per liter, keep those units on it, and there we go. All right, I know this is a long video. I'm just going to do one more kind of piece of notes in there. This is kind of just summing up everything. So measuring equilibrium concentrations. So the equilibrium constant Kc is calculated by substituting the equilibrium concentrations into our equilibrium expression. So you always have to have those numbers at equilibrium to find our Kc. Experimentally, this means that a reaction mixture must come to equilibrium, at which point one or more properties are then measured. So the different properties we can measure to know that it's at equilibrium is color. So if it's all staying at the same color, we can check pH in the aqueous solution. We can check the pressure of gases. Okay, once those are evened out, then we know that's at equilibrium. From these measurements, the concentration of reactant substances can usually be determined. Okay, and it's not necessary to measure all the concentrations in the mixture, because we can then determine them if we know the initial concentrations and the concentration of one reactant or product at equilibrium. Okay, the outcomes, so like what it kind of says, like when I'm teaching you this, what you have to calculate. So calculate equilibrium constants and concentrations for homogeneous systems. So again, that means that they're all in gas state, or they'll be all in aqueous state, somewhere where they're all the same state. And as Braun said, Lowry acids and bases, we'll worry about these. That's in chapter 16. We'll do these, but they're the same thing. Now we're just going to work with acids and bases. Okay, and the different calculations you have to know. So if the concentrations at equilibrium are known, okay, those are really easy. That's what we did on assignment 3.1. Okay, if our initial concentration and one equilibrium concentration are known, so we can do these using the ICE table. Or if the equilibrium constant's known and one equilibrium concentration are known. So again, using the ICE table, that's the one where we did like out of our textbook, where we had the x squared over 4 minus x squared. Okay, we knew the equilibrium constant, we knew one of the concentrations, so then we could work backwards to solve for x. Okay, examples that require the application of quadratic equation are excluded, so you don't have to use anything. You'll use the rule of 1000 if you're worried about using a quadratic equation. And you may use this method when responding to open-ended questions. So again, that's just in some cases it might say would you use a quadratic equation or something like this. Nice thing is you don't have to worry about a diploma and stuff, and I'm not going to try and trick you, so you'll never see that. All right, if you want any more examples, again, feel free to come into a Google Hangout. Okay, we can go over, like, I'm happy, I'll do the whole assignment with you if you want. Okay, and like, just one thing, I know some of you are nervous about Google Hangouts and things like that. You don't have to put your, like, turn on your camera. As long as you can see me and the examples I'm doing on the board, okay, that's all you kind of need. So all you need is some audio so you can ask questions, and then you just sit there and kind of watch me do my thing, similar to what these videos are like. All right.